a small present as well. Thank you very much. Thank you. I'm glad to invite on stage now the last presenter for the opening session, Giuseppe Quaranta from Politecnico di Milano.
Okay, so thank you very much to EASA for inviting me. Today I will present this this presentation on certification by simulation for Rotorcraft. This is an effort that has been going in the last 3 years. I've been leading a group of people. Here you can see the team, the group of people that supported me and the whole group in the development of this certification by simulation set. So myself and of course the group from Politecnico di Milano, but we have also people coming from NLR, from DLR, from Cranfield University and University of Liverpool. With the support of Leonardo, that has been very supporting to the activity, providing data and all was needed to develop the work, and the support and the supervision of EASA. So what is really the idea or the goal of the project ROCS? The idea was, and it still is, to develop a set of guidelines agreed with the certification authorities, applicable to helicopter and tilt rotors, to develop a standardized application of flight simulation for certification. The goal is to really make possible to use simulation as a mean of compliance for flight certification. In principle, there is nothing new in this. I mean, as far as you are able to ensure, as the CS are saying, the equivalent level of accuracy, you can always use simulation instead, or numerical analytical model instead of flight testing to show your compliance with certification rules. This is written in the standard, but the application of this idea is not always easy. And the reason why, or one of the reasons why, is really related to the fact that there are no standard guidelines, so there are no standard process that could be followed by the applicants, and standard process that could be checked by the authorities in order to verify that all work is done in the same way, ensuring the same and equivalent level of accuracy. What is the main hurdle? So I'm not going to go, through the details. I guess we are already late, and there is the guideline, and I support your possibility to read the guidelines and see really what is included. So I will go through just some crucial points. So the main hurdle is written here, and it's written in this sentence, and I really don't know who made this sentence, but I guess the majority of the people here, including myself probably, would agree with this sentence. No one of us will believe on simulation, except the person who created it. Everyone believes the flight test data, except the person who measured it. Okay? So we give a high credibility when we talk about flight testing, because we have a long experience in flight testing, and also because we always think that flight testing is reality. But we all know that you can set up a wrong test using wrong instrumentation, using wrong procedures, and getting to wrong results. Okay? So credibility is not a matter of the way you do the system you use, but is really a matter of the procedures you use. So if you're going to use the right procedures, you will have the right confidence that will provide you credibility. So if this is what we have done so far for flight testing, we need to start develop standard approaches also to do the same using simulation. So we cannot rely every time on a different approach, a different methodology that has to be checked, gone through, validated, and verified. We need to follow a standard process, because when we start doing this, this will become eventually a standard for all of us. So what is really stopping, in our opinion, the widespread application of certification by simulation is really the fact that simulation is usable, but is always considered in a limited case-by-case application. While instead the idea of developing a guidelines is really the idea of giving directions to the applicant, but giving directions also to the authorities on what is needed to be checked. So if you follow the guidelines, you have to ensure the people that the goal of reaching compliance will be reached. And the important element that the guidelines are stressing is really to define what is the sufficiency, what is the sufficient level of quality and process that has to be achieved in order to reach the goal of certifying by simulation. Adopting a standard will be also important if the standard is adopted at the industry-wide level, because this will allow an exchange of models and process. We all know that OEM most of the times rely on subsystems that are developed by other companies. So the only way to develop a good simulation model is to interact with models that are provided by suppliers that are compliant with a certain standard, because this will allow a sort of direct plug and play of the models and allow a complete simulation in principle. So if we have a standard, we can ask people to adhere to a standard, and this is really what we are looking for. Why we want to do this? Of course, we want to increase safety. We want to reduce costs. We want to reduce the duration of flight testing. Flight testing for certification is a very long process, and we want to increase effectiveness of flight testing. The precise control you can have in the flight condition in a simulator is something unachievable in a flight test. So this is an advantage that can give you a lot of points when you try to perform a certification test. So in the end, the goal is really the goal that Mr. Mueller was talking about before. So it's really the reduction of time to market to introduce innovations, because innovations will mean an increase of safety, and so in the end will mean to save life. And this is probably all we need to do. Those are the phases. So we developed the process, and the process is detailed in a document that is free and downloadable by everybody, that is called Guidelines for Certification by Simulation. As you go through the document, you will see that it is organized basically in 5 phases. You have an initial phase of project management, a second phase that is crucial, that is called requirement capturing. There is no one model that is good for all. You need to develop a simulation model that is specifically tailored on the requirements of what you're gonna do. The second phase is the phase where you really develop systems. So you develop your flight simulation model, you develop your flight simulator, and you develop also your flight test campaign that produce data that are necessary to validate the model and the flight simulator. And finally, the third phase is the assessment of credibility. You develop a model, you have to show that your model is credible. You have to show that your model has the quality that is good enough. This is a more complex show of the same phases. This is here just to show all the details that are required. So I'm not going to go through all phases, of course, but I just want to tell you that phase 1 is crucial, and you see that is really, the requirement capture is really at the center of this picture. But then phase 2 is composed by 3, let's say, building blocks. One is the validation, verification, and development of the flight simulation model. That is the yellow one. The other one is really the development of the flight simulator. Whenever the flight simulator is necessary, means that whenever a piloting loop is required, and so to provide some cues to a pilot is required. And the third important element is the development, again, of the flight test campaign that will provide data to validate both the flight simulation model and the flight simulator. Then, with probably a lot of iterations between all those blocks. You will end up in performing your credibility assessment, and if the credibility assessment is fine, you will go into a certification. So requirement capturing. Requirement capturing really starts by knowing what is the certification standard, what are the means of compliance, what are the design requirements, and out of this you will end up in setting few crucial elements that will really influence the whole process. The influence level of the model, the structure and complexity of the flight simulator, the structure and complexity of the flight simulation model, the domain of validation, the flight test campaign that has to be performed, and the amount of extrapolation eventually to be used. This will, in the end up in setting the complexity, the effort, the resources that are required, the cost, the expertise that you will need to go through the process, and the time required. So the requirement capturing phase is really the crucial part, because it's there where you set up if you're going to be able to reach the goal or not. Influence level. First important element, you have to know from the beginning what is the level of influence of the decision taken by using the model. We define 4 different levels. The first one is called the risking, where you use simply the model to get accustomed with the certification phase that in the end is going to be performed fully by real flight test. Or you have a critical point analysis where you use simulation to select some few critical conditions that have to be tested in flight. Partial credit, where you use flight simulation to get credits for some of the part of the ACR, or full credit, where the simulation is really substituting the flight testing. We understand that the higher is the influence level, the higher is the risk of using simulation. So we have to account for this increase of risk in the way we assess credibility. The second important element to establish when you do your requirement capturing phase is the definition of the domains. The first domain that has to be really clear to the developer of models is what we call as the domain of physical reality. You develop a model that is based on mathematics, is based on equations. The equations represent a certain part of the physics. We are not modeling everything. So we know what we are neglecting, and by knowing what we are neglecting, we know what areas of the flight envelope are represented in our model, and what areas are outside the capability of our model. This has to be always clear. So validation, the domain of validation, has to be well within the domain of physical reality of the model, and the domain of validation is the domain of points that are flight tested to compare the flight model with the flight test. Then we have a domain of prediction, and the domain of prediction is the blue one, and is the domain where we're going to apply the certification by simulation. So it may happen that the domain of prediction is well within the domain of validation, but it may happen that the domain of prediction has some portion that are outside the domain of validation. In this case, we are basically using the models, specifically physics-based model, to extrapolate. So the difference between the two will be called the domain of extrapolation. The knowledge of the domain will help us in understanding what is the predictability levels of the models. So we defined also here 4 predictability models. A full interpolation, where you move your model within the domain of validation, an interpolation in the domain of validation, and a limited extrapolation in the domain of extrapolation, P2, an extended extrapolation in the domain of extrapolation, P3, or a full extrapolation. We know that there are cases where we use simulation, for instance, in failure testing, for cases that cannot be flight tested. So those are full extrapolation cases. And so we need to take care about the high level of credibility that we need in order to perform this full extrapolation. So whenever you set up your level in terms of predictability level and influence level, you will end up, in one of those boxes. And so you will have a clear understanding of what is the effort required, what is the complexity required, what is the validation required for your model. And so in the end, you can really plan your certification by simulation flight test campaign. Models. I'm not going to dwell too much on models. In principle, models should be always built in a building block approach. So having different levels, going from the system level up to the individual parts. In principle, we should perform, for sure, validation at the system level, but if we want to use extrapolation and so go beyond the domain of validation, we need to perform some validation also at the subsystem levels. How many levels and how to connect them is up to the objective. So there is no general rule, but this again has to be stated clearly when you set up the requirements, because this will have an impact on the possibility to use your model in one way or the other. Verification and validation. Verification means is the model solving the equations right? So it's something that is really related to software. Most of the time, we are not asking to our software providers to provide verification. But this is a very important element. Whenever you buy an instrument for a flight testing, you want the provider of the instrument to provide you with data for the calibration of the model that has to show that the calibration has been performed in a certain condition, so on and so forth. Why we are not doing the same for software producers? So we need to see that the models are correctly verified. The second step, and this is something we really need to do, is validation. And validation is checking that we are solving the right equations, so that we are solving the right problem that represents reality. So in this case, the problem is really comparing the model with the reality. The comparison could be done at the experimental level, comparing with flight tests of the aircraft of interest, could be done with comparing the results with similar aircraft. In some cases, this is acceptable. Could be done comparing with more sophisticated numerical models that maybe cannot run in real time, or in some cases, even engineering judgment could be sufficient. We have to keep in mind that we can never prove a model to be valid. So validation is really a matter of convincing and demonstrating to your peers that your model doesn't have invalid elements. So this is crucial. You can keep going in validation if you keep continuing. So you need to set a stop. And to set a stop, what is really crucial is to understand how to scale the errors. So I'm not going to go through mathematics, but really what you may understand that is the error, that is the difference between an experimental measured value that is affected by error and a numerical simulation value that is affected by error, has to be bounded by the uncertainty of your model. And the uncertainty of your model is defined by the uncertainty of the numerical algorithm that you're using, by the uncertainty of the input data that you're using, how precise are the data that you're using, and on the uncertainty of the experimental data, because they are also affected by uncertainty. So putting together these uncertainties, we will end up in having a scale that is not general, but is case by case, that will give us a way to compare the error with the uncertainty. So if the error is much larger than the uncertainty, there is something wrong in our model. So we need to improve the models. If the error is comparable with the uncertainty, then we reach the goal. We have a sufficient level. We don't need to go over that because we don't have the data. We don't have the model. We don't have the equations to do better. So we will keep rotating about an element that we cannot really improve. So this has to be done on flight simulation model, but of course the same process has to be followed also on the flight simulator, and so on what is required to give cues to the pilot. Again, here it is important to understand what are the relevant cues for each maneuver, and just develop a simulator that is able to provide those cues, keeping in mind that here the objective is not training. The objective is really to put the pilot into a condition where he can perform the flight, the flight exactly as he will, or as much as possible exactly as he will in flight. So in some cases, we can provide cues in a different way, because again, it's not training, but that goes through the same perception, and this can give the pilot the right way of performing the maneuver, and so assess the performances. That is the objective. On the flight test, I have already talked, so I will not bother you about the importance of developing a flight test campaign that has to be tailored for model development. The last point is credibility. So how we assess credibility and what is important. We decided to use the confidence ratio as a method to assess credibility. That is the ratio that exists between the distance between the simulation model and the performance requirement that is set by the standard, and the uncertainty. So the minimum you want to have is that the margin between the simulation and the performance requirement is larger than the uncertainty. Okay? So the confidence ratio has to be at minimum larger than 1, and this will give us a low confidence. If you set a higher level, then you can increase your model from a low confidence model into a medium confidence model, or maybe a high confidence model, or a very high confidence model. So those levels could be set in our matrix where we have predictability and influence level to set the minimum requirement in terms of credibility, and so in terms of confidence ratio that has to be assured by each model. So if we're going to use interpolation for the risking, probably a low confidence is sufficient. But if we're going to use full extrapolation for full credit, probably we need a very high confidence. It means that we cannot have a model that shows results that are very close to the margin, because then we are handing in the uncertainty band. So if this is the performance requirement, remember that we need to take some margin to reduce the risk. So the higher is the risk, the higher has to be this margin. At the same time, we know that there are a lot of what we call as unknown unknowns, human errors, wrong modeling of the physics. So the more you move rightward, the more you move into an interpolation, the more could be the effect of those unknown unknowns. And so the higher has to be, again, another margin that we have to take to keep into account the unknown unknowns. This will mean that the real margin for us, the real performance requirement to be used in the model is not the red line, but is the purple line. So if this is the case, we need to show that our simulation result plus the uncertainty is within the limits, included the risk and unknown bands that we have to take. And those bands have to be larger and larger, the higher is the risk. Okay. So in the end, will be Rotorcraft certification by simulation a piece of cake? Of course, no. Okay. Initial application probably will require a significant investment and may not full payback in the short term, especially for OEMs that have a long and tradition and experience in flight testing. There are a lot of systems, procedures, methods, expertise to develop. However, we have all to keep in mind that helicopters are long life cycle programs, and we believe that the application of Rotorcraft certification by simulation will be rewarding in the long run. This is a short comparison of what we expect to be the cost of application of a certification by simulation or a certification by flight test. The flight test is the red line, the certification by simulation is the blue line. So probably we have this point in time that is the maiden flight, and so if we arrive to the point of certification, the first time we apply certification by simulation, probably the cost incurred by standard certification will be lower by flight testing. But maybe then we move to certification of applications. And now the increase of cost that we will get into by using simulation will be probably much smaller than the increase of costs of going flight testing. So simulation will become rewarding. And then you're going to develop your second version of the helicopter, the second family. And there, the advancement in terms of reduction of costs will be significant. And then on the next generation, the experience built on certification by simulation will really build up in reducing the costs. So it's a process. It's not something that will come in a second, but it will arrive. So with this, I will conclude. I just want to tell you that tomorrow, the whole day, we're going to have a workshop to show some applications of this idea that will be running on room A in this area, starting at 9. So if you want to join, let me know. And also, I want you to know that the guidelines are public, so you can download, and we will be very happy to receive feedback on the guidelines in order to improve the quality of what we've done. So thank you very much.